Assalamu alaikum warahmatullah. My name is Abdulaziz Mahmoud Hussein, and today I'm going to be explaining my project for control system course. I'm going to be sharing my screen right now. Give me a second. Yes, so I'm going to be explaining my control system course project, which was hopefully you can see my screen, which is the project modeling and controlling of a single tank liquid level system by the Dr. Muhammad Awad. The project idea was that we're going to have a water tank, which we're going to try to keep at a specific water level, water measurement by using PID controllers, ultrasonic sensor, and a water pump. The main idea of the project that we're going to have a PID controller that's going to be controlling the motor speed, which is inside the water pump. So we're going to be in that we're going to be controlling the water level going inside the water tank, and by that way we can know and we can keep a specific desired point of water level on the tank. My specific contribution to this project was that I was in charge of the hardware side of things. So I was in charge of the hardware component, connected them all together, and kind of make sure that the circuits and everything is put together properly. The circuit side of things and also the mechanical side of things. The components used for this project were the Arduino Nano, breadboard, ultrasonic sensor, batteries, IRF 520 MOSFET driver module, DC 12-volt submersive water pump, two water tanks, and water valves. We're gonna start off the connections by explaining how the Arduino is connected. So our Arduino was connected to the IRF 520, sorry, MOSFET driver. It was also connected to our MATLAB code, which had all the PID calculations and the both the manual and the adaptive PID calculations in there. And it was also getting a lot of the power from the laptop. So Arduino was the one that was connected to the MOSFET driver using the PWM pins. I believe it was pin D3. And basically, Arduino was our main microcontroller, getting our code from MATLAB and applying the code instructions to the MOSFET driver, which is connected to the water pump. The reason why we use this specific motor driver, one is that we give the right impulses and the right waves to the water pump. As you know, that we're going to need to use the PWM pins in the Arduino, get the specific output, which is the instructions to the motor driver. Instead of going straight to the motor driver, first we're going to go to instead of going straight to the water pump. First we're going to be going to the motor driver, and then from there we're going to be giving it to the water pump. And the reason why we're doing this is to kind of give the exact waves, the PWM waves to the water pump rather than connect it straight away. So if you want to control the speed of the motor, we need the PWM pin, and we're also going to need a motor driver MOSFET, this specific model we have, in order to make it a smooth transition. This is the exact one we used. Obviously, it's going to be connected to the water pump. This black pipe, in a way, is the one carrying the wires from the water pump. This is also going to be connected to the Arduino from one side. It's going to be connected to the ground, the VCC, and the signal coming from the Arduino from from the PWM pin. And that's the connections for the MOSFET driver. Next is the specific water pump we used. It's a 12-volt water pump, and it's submersive. The reason why we chose this is mainly because it was the one that was recommended from the doctor to us. Also, we chose this specific water pump because it's submersive and it gives us a 12-volt output. We had other pumps, one was 5-volt, and the water output of it was really, really slow. We had another pump and it take around like 25 volts, and that pump, the issue with it was it was pumping water at a really high level, And giving it the proper power supply was also an issue. So we chose this pump, which is obviously connected to the PWM pins as well, and that's where it is also connected to the power to get its required 12 volts. Ultrasonic sensors. The ultrasonic sensors was placed on top of the water tank so that it looks on the water level from down. The ultrasonic sensor from on top was stuck in place by using two wooden sticks, and its output, the eco pins and the trigger pins, the voltage and the ground were all connected to the Arduino, and that's where we're controlling it. That's where we're getting the inputs from it from. How the ultrasonic sensor works is it sends out waves, and when the waves hit the water and get reflected back, it takes its time, and that time is then used to calculate with the help of speed to calculate the distance. And this is how we set it up. And the reason why we chose ultrasonic sensor here is that we're going to need the water level. So in order to get the water level, the ultrasonic sensor helps get the water level, and then from there we calculate the error from the input water level from the ultrasonic sensor and the desired set point. All right. Next, the water valve. This is the specific water valve used. The good thing about this water valve is that it has a small opening. We had another water valve with a bigger opening, but that gave us issues in the PID because we had a really high uh, water flow out rate. When we got this water tank, because it's long and it has a narrow opening, the water flow rate was lower, which helped us control the PID better. How we set up the two water tanks, we had the tank set at a higher level and the one set at a lower level. The tank set at the higher level uh, was the one that had the water valve coming out of it, and it also had the reading from it. If you notice, the readings are starting from top to bottom because these are the different levels from the ultrasonic sensor to the water. So when the water is really close to the ultrasonic sensor, we're going to get example reading of 1. That means the water is 1 centimeter away from the top of the tank. Uh, Here is the pipe that was connected from the lower tank to the higher tank, and here, as I said, the tank with the water valve is connected to a higher level, and right under it, which is taking in the water output, I mean, sorry, the water flow from the valve is another tank, which inside it has a water pump. This tank, you can just say, is like a storage for excess water. So the idea is this tank has water in it. It's going to pump specific water levels to this upper tank to keep it as a specific point of water. And while that's the pumping in water, this water valve is letting some water out back into here. So we're going to have water flowing in and flowing out of the tank just to keep it at a specific level. And how we control how the water pump uh, give the right what do you call it, the water flow in rate is by the help of PID. So when the PID gets the reading from the ultrasonic sensor, it's going to calculate the error, and from the error, it's going to know the exact power to give the exact PWM signal to the water pump, so that the water pump knows exactly how much water flow should be given to the water tank. And then from there, alongside with the water coming out from the water valve, we're going to have the system set at a specific point. By the way, the water valve, we didn't open it fully, we opened it at a specific angle, which gives us the best output. So let's say if we change the opening of this valve, it's going to change our PID slightly, and it can be considered as noise. For this project, the main issues we faced was that first of all, finding the right amount of level to open the water valve to get good output. That was one of the issues. One of the challenges, I would say. I wouldn't say an issue. Obviously, the PID tuning was a challenge for us at the beginning. Next, another issue we had was the setting up of the ultrasonic sensor on top. We had to kind of find a creative way to put the ultrasonic sensor on top. and also adding the non-linear method with adaptive PID changes. That was one other challenge we faced. That was more of the one in the coding part. The hardware part of the system was good, but it wasn't complicated as much. I feel like this project was more of a hardware project rather than a more of a software project more than it was a hardware project. So the main work is gonna be done in the PID in the coding of MATLAB. But in the hardware, it's pretty much straightforward. Just the adjustment of the valve and the tank placements. That would be like the little bit of a tricky part. To analyze our output, here in this code, we set the water level to be at the desired point to be at, if I can. Yeah, we set it at 7 centimeters. So our goal is to have the water to stop at 7 centimeters, which is around here. So once we run the code, well, run the output, we're going to see that the water starts moving up slowly and surely. And here's the water tank setup I was telling you about. The lower tank with the pump is flowing water into the upper tank, trying to make it reach a specific point and stay there. The ultrasonic sensor is calculating the distance from the ultrasonic and the water level. So basically from the top of the top tank to the water level, and that distance is going to be inputted. And the difference between that specific distance and the set point is going to be considered as the error, in which you're going to be feeding it to the PID. As you can see, this is the non-linear PID working. We're going to see that as we move forward, we're going to skip a few parts. As you can see, that as we get closer to the PID, to the specific desired point, our water pump is getting a lot of signals. So you can see the frequency of this signal increases. That's because you're going to keep on giving readings to the water pump, giving it instructions to kind of maintain and reach that set point. As you can see, we're getting close to our point. Here, when we had the manual PID, here we had really high fluctuations, but when we had the non-linear PID, when we get close to it, we can kind of see that we're kind of settling around that point. Here you can see the outputs of our cycles. And like I said before, when we got really close to our desired point, our frequency of basically the input, the pump input increased. So the pump started working more. And that's it. If I can just stop at the end, our system worked, alhamdulillah, it worked really well. We're basically exactly at 7 centimeters. We have an error of around 0.3 on average, which is really good for our PID. Alhamdulillah, it was a really good project. It gave us a lot of engineering insights, and it's one of the projects that really established us as and introduced us to control systems. And even though we had other previous projects such in self-driving courses, example, where we implemented PID, but I feel like this project was really a PID heavy, and it gave us a really good idea. Thank you so much, and hopefully, Doctor, we see you in other courses. Thank you so much.